Hello, everybody. Welcome back to Monte Carlo Methods. So this random guy comes up to me in the store the other day and he says, I just love your channel. And I said, well, thank you, but you're imaginary. That never happened. This non-existent interaction is not the point, though. The point is the use of the word random. Especially in the US, people use the word random to mean out of the blue. No idea what's going on here. No rhyme or reason, no structure. In this video, we're going to define random and try to harness it and generate it. We are going to be generating and producing values or random samples from various distributions. For example, the normal distribution. Now, if we generate values from the normal distribution, we talked in a previous video about making a histogram and seeing it match a PDF. The normal distribution is, of course, the bell curve, which has most of its area or mass in the center and less out in the tails. So when we generate values, we're going to get more of them in the center and less out in the tails. And that is some kind of structure. So this is not completely random. Random sampling from a distribution, structure. However, if we just want to generate random numbers without respect to a distribution, we're really talking about a uniform distribution, either discrete or continuous. For example, if you want to generate random numbers between 1 and 15, all those integers, then you want to generate 1s and 2s and 3s up to 15. And in the long run, you want to see each number 1/15 of the time. The continuous version of this is generating numbers from a PDF that doesn't have particular high points and low points, that's flat. And yes, I mean uniform and the uniform PDF. That distribution on 1 through 15 with equally likely probability put on each of those numbers is also a uniform distribution. That's a discrete uniform distribution, and the continuous PDF that's a flat line is a continuous uniform distribution. And I just want to let you know that when I say uniform, my default is going to be the continuous distribution. Because the PDF for a uniform distribution over, say, the interval from some number A to some number B has to be a flat line, and because the total area under a PDF has to be 1, we know because the base of the PDF is of length b minus a, we know that the height of that flat line has to be 1 over b minus a. If this is the case, we say that our associated random variable x has a uniform distribution on the interval from a to b. And you can close the endpoints of that interval or close one of them and not the other. It really doesn't matter because area under a PDF at one particular point is always 0. So you can throw them in or leave them out. Of special interest to us is the uniform distribution over the interval from 0 to 1. And the reason this is of special interest to us is because we can take values generated from the uniform 0-1 distribution and transform them into values from almost any distribution you can imagine. So in Monte Carlo methods and simulation, uniform 0-1 observations of random variables are going to be like our base units for doing everything else. When I said observations there, if you start generating from a uniform 0-1 distribution, you should be outputting a list of numbers between 0 and 1. Once you have those numbers like 0.8372118, 0.2370251, I don't know, I'm obviously making these up, but once you have those numbers, you no longer have random variables. You have observations or realizations from the uniform 0-1 distribution. Other people call these variates or deviates, although be careful, a lot of people use those two words wrong in the literature. Here, I'm going to call them observations or realizations. Again, we're no longer random. We have gone through some algorithm to generate values and we have numbers. Those are our realizations from that distribution. Let's look at a histogram. Here, I have an evolving list of numbers or realizations or observations that are being generated from the uniform 0-1 distribution. We don't know how to do that yet, but we're getting there. So my first number is 0.8763857. And if I were to make a histogram of this sample of size 1, then I'm going to want to set up some bins across the interval from 0 to 1. And I'm going to choose to go with bins of width 0.1. So my bins are defined as 0 to 0.1, 0.1 to 0.2, etc. And because this first observation is 0.87 something, it falls in this bin between 0.8 and 0.9. And because this is the only observation right now in this histogram, all of the area is there. And as we discussed in a previous video, we're using density on the y-axis, which makes the area of this bar represent probability. And so basically from what we're seeing in this very exciting sample of size 1 is we believe that this generator is going to give us the number 0.876, etc., with probability 1 because we haven't seen any more values. So the base of this rectangle is 0.1, and therefore the height needs to be 10 so that the total area is 1. Next value generated by the random number generator I'm using here is 0.2607807. So when you add that to the histogram, that is over here in this bin between 0.2 and 0.3. So I get some area in a bar in my histogram. And now, based on what we're seeing, half of the values in the sample are between 0.8 and 0.9, and half of them are between 0.2 and 0.3. And so the heights of the bars have to represent that. In other words, the base of each bar is 0.1, and the height of each bar is 5. So the area of each bar is 0.5. And when you add them together, you get a total area of 1. Let's keep going. Let's speed this up a little bit. Let's generate some more values. Some things happen here, and it's not really exciting at all. This change of shape is an artifact of the chosen bin width. You'll notice in my list of numbers here, I have 2 numbers that came out between 0.7 and 0.8. So this bar is twice as high as all the other bars that just saw 1 number. But if I had made my bars go in increments of 0.05, they would still all look level because one of these numbers is 0.70 something and the other is 0.7569 something. So they would have fallen in different bars. Right now, what we're seeing is totally an artifact of the chosen bin, and we will talk more about this as this course goes on. But it's not going to matter if you look at a lot of values. Let's fast forward to 100,000 values. Here's the histogram looking nice and flat, and this looks a little silly because the y-axis is way too tall, but my goal here was to keep the y-axis constant throughout each step of this simulation. So let's rescale the y-axis. That looks a lot better, and here I have superimposed the uniform 0, 1 density. And this is 100,000 values, making a histogram, and you can see a little bit of noise here, a little above, a little below that line, but that's okay. Even if we truly are generating values from the uniform 0, 1 distribution, we can't see the distribution in full with only 100,000 values. To give you an extreme example, if you want to test whether or not a coin is fair and you flip it 3 times and you get 2 heads and 1 tail, are you really confident enough to say at that point that it's biased towards heads? You need more information. Now, in this case, we have a lot of information, but we don't have all of it. So there is going to be some variability, and we'll eventually talk about making like little confidence intervals for what to expect out of the heights of these rectangles if you truly are generating numbers from the uniform 0, 1 distribution. So how did I get this list of numbers? There are so-called true random number generators, abbreviated TRNG, and there are so-called pseudo random number generators, abbreviated PRNG. True random number generators try to harness true randomness from the physical world. This might be counting the number of particle emissions from a radioactive molecule that's decaying. This might even be physically rolling dice. And those dice may not be perfectly fair, but we are generating with a physical process. And so I'm not saying that's going to give you random numbers from a uniform distribution on 1 through 6, but maybe that's the beginning of a random number generator that can then be adjusted for any perceivable bias in the dice. A very famous example of a true random number generator was given by the Rand Corporation. Between the mid-40s and mid-50s, they spent a lot of time generating some random numbers using the physical process of radioactive decay. They had a radioactive molecule that was emitting particles, and then they had a kind of gate in front of it that would open and close at deterministic, non-random times. Now, when it was open, a particle could come through, maybe more than one, or no particles could come through. If they saw at least one particle coming through, they recorded a 1, and if they saw no particles coming through, they recorded a 0, and then the gate kept continuing, opening and closing, and they would get a list of 1s and 0s that they could turn into binary numbers, either integers or decimals. The RAND Corporation had a re-randomization step at that point because when they studied the output, and they made a table that took 10 years, when they studied the output, they noticed a little bit of correlation between the numbers. When you're trying to generate random numbers in a certain interval, either discrete or continuous, one assumption is that you're generating uniformly from a discrete or continuous set. And the second assumption is that the numbers you're generating are independent of each other, that there's no kind of correlation as you go. So you've heard maybe in probability and statistics, the acronym IID, which stands for independent and identically distributed. And what we want out of a random number generator is to generate IID, uniform 0, 1 random variables, or maybe integers from a set like 1 through 15. The RAND Corporation published a book of these numbers that is available to this day on Amazon. It is called A Million Random Digits with 100,000 Normal Deviates, so 100,000 draws from a normal distribution. The book is a page turner. It keeps you on your toes the whole time you're reading the book. You never know what's coming next. And the reviews on Amazon are awesome. In the description box below, I'm going to put a link to the RAND Corporation's page where they describe the random number generator and the whole process and the 10 years they spent on it. And it's a really interesting read. So I mentioned a couple of kinds of random number generators. One was a true random number generator that takes advantage of some kind of random physical process. But the second was a pseudo random number generator. And this is an algorithm that your software is going to use to generate random numbers. Now, like most algorithms, there is a step, and then you do this, and then you do this, and then you loop back around and you start again. And that sounds anything but random. But if you do it well, you can mimic randomness, you can mimic uniformity and even independence out of a deterministic algorithm that is just giving you numbers in, well, an algorithm. So the output of these algorithms in most built-in software is called a pseudo-random number generator because they're not completely random and they're not completely independent. But again, the game to play is to make them look that way. We're going to be using pseudo-random number generators in here. And after this video, I'm going to stop calling them pseudo. We're going to call them just random number generators, but keep that way in the back of your mind. Yes, they are generated by an algorithm, but we're going to see that the results will pass many tests for uniformity and independence. The first pseudo-random number generator was attributed to John von Neumann in the mid-1940s. It was known as a middle square method. So you took an integer of a certain length, preferably a larger length, let's say 4 digits, and you square it. And if you square a 4-digit integer, you can get 6, 7, and 8-digit integers. In other words, if I square 9999, I get a number that's 8 digits. So squaring a 4-digit integer, if you fill it in so that it has 8 digits by putting in a leading 0, then we have always 8-digit integers coming out of this. So let me just give you an example. Starting with the number 2321. If you square that, you get 5,387,041. This has 7 digits, but I'm going to write it as 053877041. Now it has 8 digits, and we started with a 4-digit number. I'm going to grab the middle 4 digits. In this case, that's 3870. So starting with 2321, we have produced this other 4-digit number, 3870, and you continue in this manner. You square that, you make sure it has 8 digits, you put some leading zeros in if needed, and you grab the middle 4. And this is generating a list of numbers. Are they completely random? Was this a good random integer generator over a certain region? We're gonna look at that later, but This was the first known example of a pseudo-random number generator. For a long time, so-called linear congruential random number generators were the norm. The first was proposed by Derek Henry Lever in 1949, and linear congruential random number generators were the most commonly used random number generators in computers and software until they were in a lot of use until the late 90s, actually. Linear congruential random number generators are based on modular arithmetic. Take two non-negative integers a and b. Let's take a look at this expression. You read this a mod b, and the result of this expression should be you look at how many times b divides evenly into a, and then you return the remainder. For example, 7 mod 2 is 1 because there's a remainder of 1 when you divide 2 into 7. 8 mod 2 is 0 because it goes evenly into 8. So you can divide 2 into 8 and there's 0 remainder. Let's look at another one. 8 mod 3, 3, 6. I can't go up to 9. I've gone too far. So 3 goes into 8 twice, and then we're left with a remainder of 2. So that's the answer when you write down an expression like this, 8 mod 3. One more example, 7 mod 9. 9 does not go into 7 at all. So there are no kind of whole multiples of 9, and the entire value 7 is the remainder. So 7 mod 9 is 7. You can see that these sort of modular operations will always give you numbers between and including 0 and b minus 1. So let me say it a little better. If you're doing a mod 3 operation, your results could be 0, 1, or 2. Whereas if you're doing a mod 9 operation, your results could be 0, 1, 2, 3, 4, 5, 6, 7, or 8. With that, we're ready to define the linear congruential random number generator. In order to run one, you need to choose 3 integers. One of them we're going to call m for modulus. This is going to be the number we're modding out. M has to be positive, and we'll see that we actually want this to be quite large. Then you have to choose an integer a, which is known as a multiplier, and a is an integer taking on either value 0, 1, 2, 3, up to m minus 1. You then have to choose an integer b, which is known as an increment, and that also needs to come from the set 0, 1, 2, 3, up to m minus 1. Finally, I know I said you needed 3, but you need to choose a starting value for what's going to be recursion. This is known as a seed for the random number generator. Because I'm going to make a sequence of numbers x0, x1, x2, x3, I'm going to call this seed x0, and this needs to be an integer, which could be, again, in the set 0, 1, 2, up to m minus 1. Once you've chosen these, you have x0, a starting number for your sequence that you're going to produce, and you produce xn by taking a times the previous x, adding b, taking that whole quantity, and modding out m. We'll see an example in a moment. This is going to produce integers between 0 and m minus 1. And if your goal is to uniformly produce integers in a certain set of integers, this might be okay. I doubt it would be uniform and independent looking. We'll get back to that in a second. But if your goal is to produce a continuous uniform number between 0 and 1, you take whatever comes out of this algorithm. After you make the whole list, you divide everything by m, and those will be real numbers between 0 and 1. And you must think I'm kidding at this point. You must think I'm making a joke. This does not seem to be a list of randomly generated uniform numbers, certainly not independent. It's a very cranky algorithm. Plug in a number, get out a number, plug in that number, get out a number. I can't imagine this would do well. And it depends on your choices for the parameters. Let's just look at a really small example here. If I let x0, my seed, be 0, and my multiplier a be 1, my increment b to be 2, and my modulus m to be 3, then x1 is going to be a times x0 plus b, and that's 2. And when you mod out 3, 3 does not go into 2, so 2 is the entire remainder. I'm going to plug that number into the formula again. So I've got my A times 2 plus B, and that's 4. And when you mod out 3, you get the remainder of 1. I'm going to plug 1 in again. So I get A times 1 plus B, and that's 3. And when you mod out 3, you get 0. And I'm going to plug in 0. Wait a minute, I started with a 0. So clearly, I'm just going to start repeating this sequence and get 0, 2, 1, 0, 2, 1, 0, 2, 1. And if I divide by m, which is 3 here, I end up with 0, 2/3, 1/3, 0, 2/3, 1/3. And that seems very far from random, especially if I'm going for the continuous uniform distribution on 0 to 1. So at first glance, this algorithm, the linear congruential random number generator, seems absolutely ridiculous. But if you have good choices for the parameters m, a, and b, and sometimes the seed, you can actually mimic randomness pretty well and even independence. We are going to run some of these linear congruential random number generators and run some statistical tests for uniformity and independence. Clearly, you want m to be large if you're trying to get something in the continuous uniform distribution from 0 to 1. You don't just want 4 different numbers being repeated over and over again. You want to get as many as you can. So large m is super important. But you also need to pay attention to the a and b and even the relationship with the m you chose. There was a really famous example of a random number generator called RandU that was developed by IBM, I believe in the 60s. I'll double check that and I'll put it somewhere here in this video if I was wrong. It was a linear congruential random number generator, which I just claimed could do a good job for good choices of A, B, and M, and even a seed. So IBM proposed taking A to be 2 to the 16th plus 3, B to be 0, M to be 2 to the 31st, which is quite large, which means we're going to get a lot of numbers in the interval from 0 to 1 when we do the ultimate division, and choosing the seed x0 to be odd. So I ran this algorithm not using a random number generator by IBM. I just programmed the linear congruential random number generator. I generated 100,000 values, and here you can see the resulting histogram, which looks pretty good. I can't tell you anything right at this point about independence. We're getting there, but this looks like a uniform distribution. And we know that we're not going to see repetition because of that large modulus, or not very likely. It does depend on all 3 parameters. But what if I took these numbers that it generated and made ordered pairs out of them? So I made a pair using the first number and the second number, and then the third number and the fourth number, and then the fifth number and the sixth number. What if I plotted those in 2 dimensions? What do you expect to see? I expect to see a cloud of points in the unit square, no structure, and it looks pretty good. Let's try again for triples. The first number, second number, and third number is going to make a 3-dimensional point, and the fourth number, fifth number, and sixth number is going to make another 3-dimensional point, etc. I'm going to plot these in the unit cube. And that also looks kind of like a fuzzy cloud, not so bad. But watch as I start to rotate this cube. Wow, something is really wrong with this random number generator. In fact, we can prove and we can see that all of the points in this 3-dimensional cube are falling on one of 15 hyperplanes. This wasn't noticed for a long time. RandU was used throughout the 60s and 70s, and even later in some cases. And it passed tests for uniformity and independence, the ones we're going to look at, and no one caught this for a long time, but this is really bad in terms of randomness and uniformity. There is a lot of structure peeking out here. So you really have to be careful with your choice of A, B, and M, and there were entire PhD theses in the 70s, hundreds of pages devoted to how do you choose A, B, and M. Lots of advice is given, for example, that you want B and M to be relatively prime, and etc. George Marsaglia proved that any linear congruential random number generator will have the same fate of being restricted to hyperplanes in any sort of higher dimensional cube you want to look at. But if there are a whole lot of hyperplanes, it's kind of unnoticeable. We've moved on from linear congruential random number generators. The most popular generator, arguably, being used in software right now, including R and Python, is called the Mersenne twister. We're going to talk about the Mersenne twister and how it works. It is a so-called bit shifting algorithm, and I'm going to make sense of those words to you, hopefully, in the next video. So I hope to see you there.